Hello everyone, and welcome to today's webinar where I'll be talking about trains in Dialog APL, the train function syntax. Those of you who are watching live on dialog.tv can participate in the chat below. And you can give your comments in the chat below, and Adam behind the camera will be able to talk with you and send some of your comments and questions to me throughout this webinar. The train syntax itself is not especially new. It's about 6 years old in Dialog, and the idea itself is even older than that. So it was introduced to Dialog in version 14, and the first link in the description below is a video of John Scholes at a user meeting introducing the train syntax as it exists in Dialog today. But trains have existed in the J programming language since it came about in 1990. So it took something, I suppose, like 24 years for that to come into APL, back into APL. But anyway, I'm going to be talking to you about what trains are, how to read them, how to write them, and some of the benefits of using them and some of the times that you might want to avoid them. So before we talk about some details about trains, I'd like to give you a little bit of history. So with traditional mathematical notation, here denoted TMN, and in APL as well, in the beginning we had the expression, and the expression was good. But the developers of APL realized that traditional mathematics had some more notation that would be quite useful for APL. For example, function composition. And function composition was brought in to APL in quite an elegant way using the exact same JOT notation. But it's not just composition you can do between functions. You can also do things like multiply functions, add them together, divide them. And implementing this behavior in APL proved somewhat of a challenge for the developers, because while the symbol here for multiply is the same as the function symbol multiply in this case, and in APL that's a dyadic scalar function, here it's not actually acting as that function, it's acting as an operator, binding f and g and creating this other function which has the behavior of applying f to the argument, applying the function g to the argument, and then multiplying those results together. And so the language developers were racking their brains about how to put this into APL with the right to left consistent syntax, and they considered things like maybe you'd have a pair of operators that act, say, between, so you have f operator times, and then another operator, and then g, and then that would bind the three functions together to create this behavior. They started to settle in maybe on the idea of having an extra set of operators which looked like the function symbols that they came from but with an overbar, and this idea could have been okay, but you have the issues such as, okay, now we have to put a bunch more symbols into our notation. We have to use up space on the keyboard, which is obviously very valuable. You're limiting the number of functions that you can do this type of composition with, and some of the functions themselves could prove to be quite problematic. So yeah, the language implementers are racking their brains trying to decide how to do this, and one fateful plane ride, Ken Iverson wakes up from a nap with a realization, and that realization is boom. Right? I mean, it's astounding. With the benefit of our hindsight and the fact that this already exists when I've come to see it, it looks kind of obvious, but it's amazing that once again APL has managed to bring in some notation from traditional mathematics and integrate it quite nicely into their consistent machine executable language. Not only do we have another bit of traditional mathematics appearing in APL, like we do with many of the primitive symbols that are used, But also coincidentally, they were able to merge two seemingly disparate pieces of traditional mathematical notation. Namely, in this example, the plus minus thing, function or whatever it is, notation, once again unifying some disparate pieces of notation. So, and at the top here we can see some information about the valence. So from now I'm going to go into the session and run a demo script just so that I can interact a bit more as I talk you through some of the details. So to start with, let's look at calling trains. Much like any APL functions, trains can be called monadically with a single argument on the right, or dyadically. The important thing for trains is that the functions, the group of functions, as it's written, are isolated from the arguments. So what this means in this example is that this expression is not a train. This is just vanilla flavor APL. So paths from right to left, we have negate 2. We take the ravel of negate 2, creating a one element vector, and then we do 4 plus this. So we can see in the end our result is a one element vector which contains the number 2. To make this a train, we can isolate the function from the arguments using parentheses. Now we get 4 plus 2 catenated with 4 minus 2. We can also isolate the function by giving it a name and then applying the function using its name. Now, when you see trains out in the wild, it's likely that you'll see this type, inline anonymous trains. You'll likely only see this type when it's a very short train, maybe 3 to 5 functions, and it's either a very well-known idiomatic train, we'll see a couple of examples, I mean plus or minus is one example, or it's so short and clear that it's easy for another person to read. Assigning trains like this, you might see if you're building functions up or someone's constructing a function out of sub-functions and the overall structure just happens to match this pattern. This happens quite a lot of the time. But it's not just primitive functions, as we've seen here, that can go into trains. You can use any named functions. So I'm going to do an example here where we have a tacit definition of the sum plus reduction. We can create a tradfun for divide. Oops. Let's see, R gets X divide Y. Right, a little bit trivial, but there you go. And you can even have a defin in there. And so you can construct your train using the same structure, so 3 functions juxtaposed next to each other. And here we have a train which calculates the mean average of a list of numbers. And it has to be a list, I think, in this case, because of this somewhat convoluted count function. So that's how to apply them. Let's look at how to read trains, an overview, and then we'll do some more details. How to read. There are 2 types of trains. A 2 train is in a top. So for example, here is a juxtaposition of 2 monadic functions that finds the maximum length vector in a nested vector. So we have 2 functions here that both happen to be derived, so count each and then the maximum. Here's a dyadic atop, a dyadic 2 train. This one I've named wherein because this one asks wherein my text is my left argument. And here we can see that this, the left argument, is found at position 4 and position 14 of the right argument. A 3 train is a fork. So all trains are either 2 trains, atops, or 3 trains, forks. And anything longer is simply a 2 train or a 3 train where the tines, the individual pieces of the train, are also functions which could be defins, tradfins, primitives, or more trains. So So here's an example, which is the range. It's the maximum value minus the minimum value. This one comes out quite nicely. Also, the left tine of a fork can be an array. So in this case we have, the exclusive difference, or is it, the difference between 5 and 10, not including 5 and 10. Or monadically, we have the inverse probability. So if the probability of something happening is a quarter, the probability of it not happening is 3/4. But the left tine of a top cannot be an array. That's a syntax error. Okay. There's one more thing to discuss before we look at some examples of reading trains, and that's addressing arguments. Even though the train syntax is a form of tacit programming, so you don't explicitly refer to the arguments, like in tradfins you name the arguments and refer to them that way, or in dfins you have sort of symbolic referencing using alpha and omega. In trains you have no reference to the arguments, but sometimes you want the argument, and this is where the tacks come in. Deceptively simple functions, the left tack returns its left argument unchanged, and the right tack returns its right argument. They're very similar to these two dfins, and we can use this similarity later to convert from dfins into trains, and I'll show you how to do that. So let's look at an example now. Here's the train from a slide at the beginning of just now. Some of you might recognize it as a slight modification on a pretty quintessential classic train that gets shown all the time when people introduce modern APL. It's the sum divided by the count, and I also defined it using different functions a second ago. The issue with this one is that because by default in Dialog 0 divided by 0 returns 1, this version of the mean average gives the average of an empty vector as 1, and some people don't want that behavior, so we can modify it slightly. So now with our one ceiling we return 0. Some people don't even, are concerned that 0 divided by 0 returns 1, and you can make a version that returns a domain error on an empty array by binding times with divide, so that the interpreter has to do divide by 0 first and generate the domain error. When it comes to reading this, let's take it down. Trains are grouped in threes from the right, making a series of nested forks until you have one function left or no functions left. And if you have one function left, then you have an atop, because you have one function and then another function, which is a fork, possibly made of other functions. Well, definitely made of other functions. So we go from right to left and we can see function, function, array. We said a second ago that the left tine of a fork can be an array, so this becomes a fork. So this becomes one whole function. So we've got one function, two functions, three functions, because the operator binds to plus to make a single function. So here we have a fork that's made out of one derived function, another primitive function, and another fork. Let's try that method again using a slightly longer train. Oops. So on its own, we can go from right to left. We have function, function, function. Group these together. This whole thing becomes one function. We've got two functions, three functions. Can group these together. This whole thing becomes one big function. Two functions, three functions. We combine these, group these together. Okay? And we have some training wheels to help you in the interpreter. If you turn boxing on with the minus trains equals parens option, then the interpreter can wrap trains in parentheses in a similar way to help you pick out and find which parts are grouped together using this rule. Of course, what you've seen up till now is the tree display of a train, and the thing about this is that the way that trains are defined in Dialog APL completely reflects the way that APL functions are passed normally. You either have monadic functions, this is one function applied to whatever's on the right, or you have dyadic functions which apply between arguments. And trains have this exact same structure. So in this case it would be like a monadic function applied to one big dyadic function. Monadic function, alpha, dyadic function, omega. Hopefully this will become a bit more clear as I go through a couple of examples. But to summarize, reading trains. There are two types of trains, the tops and forks, 2 trains and 3 trains. All of the trains are of these type. In a monadic case, a 2 train. For a 2 train, the left function applies to the result of the right function applied to the argument. In the dyadic case, the left function g applies to the result of the right-hand function which is applied dyadically between arguments. A 3 train is a fork. The middle function is applied between the results of our outer functions applied to our argument. Similarly, in the dyadic case, middle function applied to the result of the outer functions applied between. The left hind of a fork can be an array, and someone quite clever once told me if it's written down, you don't have to remember it. So this information is available if you search for APL Wiki trains, go to the APL Wiki and find our entry on trains, and this information is there for you to refer to later. So that's how to read trains. Now let's look at how you can go about writing trains, especially the well-defined little ones. They seem a bit esoterical. How did someone even come up with this? But I'll show you a couple of methods to help you on your way. If you want to consider, do I want this bit of APL, do I want it to be a train? The likelihood is that you've already expressed your solution, or whatever your statement is, as either a one-liner of traditional APL or as a one-line defin. And there are a couple of ways to convert those into trains. I'm going to start by talking about converting defins to trains, because on the defins website there's a page that you can find, and there it expresses a whole algorithm which applied to a single line defin can turn it into a tacit train. I'm going to show you a couple of simple examples, but you can go on that page if you want to find out more details. So this is a single line defin. It's very simple. It finds the largest multiple of the left argument, which is less than the right argument. Okay? To start our procedure, let's replace our curly braces with round parentheses. So now it's going to become a train. Let's go from right to left, grouping functions into 3s. So omega becomes one function like this, which refers to the right argument. There's a second function, and then we have alpha, the third function. So this whole thing becomes a fork. Then this is one big function, 2 functions, and then omega is also a third function here. So the overall structure is a fork. And then we can use our similarities from before to replace all our omegas with right tacks and our alphas with left tacks. And here we have a train version. There's one more simplification that's worth mentioning now. If we have left tack function right tack, then this applies exactly the same as the function written by itself. So now we've simplified our fork down, and we have something which actually looks kind of neat. Let's do one more, slightly more involved example, but hopefully you'll recognize this one already. So once again, change our curly braces. We can already see the fork structure ahead of us, right? On the right, we can make that a defin, and on the left, surround that as a defin. And then we can go into each of these defins and deconstruct them again into the trains. So plus slash omega like this, and that omega can turn into a right tack. And on this side, let's do the same sort of thing. Replace our curly braces. Now we want to look carefully at this one because there are a few more symbols. So function, 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 except this tally is applied monadically. So really this isn't a top. But once again, we can replace our omega with a right tack and our function still works. So we have function, function, function. That makes a tray of a fork. And since we have a fork inside a fork, we can actually simplify this by taking away a couple of parentheses. Same on the left, we definitely have unnecessary parentheses now. And here we have, I think this is about as far as we can go with this defun and still retain the exact same functionality. What I mean is, the defun, by referring to omega, ignores its left argument, as does the train that we've just made. But if we knew that we were only ever going to see this train applied monadically and it was never going to see an array on the left hand side, we could simplify further by getting rid of our right tacks here. The function still works. However, if we put an array on the left, we get something completely different. This is because now our odd numbered functions are applied dyadically. So instead of tally, this becomes not match. So 3 not match. Our right argument is 1. 1, the greater of 1 and 1 is 1. And then we have the windowed reduction, the windowed sum of our right argument. So 3 plus 1 plus 4 is 8. 1 plus 4 plus 1 is 6. 4 plus 1 plus 5 is 10. So yeah, this is one thing to watch out for. Be a little bit careful. So, as I was trying to express earlier, the train syntax reflects function application in vanilla APL. And we can use that fact along with the tree structure. How's this? We'll get away with it. To turn even a normal sort of old school-ish, I guess you'd call it, more traditional looking APL one-line expression into tacit form. So hopefully by going through the example, what I mean becomes a bit clearer. In this case, we have a function which is a function of list, but list is assigned in line. Well, what we can do is comment out the assignment and just pretend that list has already been defined, which in this case it has. And we know that list is the only argument here, it's the only thing named, so let's just assume that's going to be our one single right argument. And go through and let's look at the sort of structure of this so that we can turn it into a train. I can already sort of see a fork here. We have something on the left and a middle function and a reference to our argument on the right. So what I'm going to say, I'll do this with pen and paper, on the outermost level we have a fork where the middle tine is partition. On the right hand side is a reference to our argument, so we're going to use our right identity function, right tack. Over on the left we have another fork, so we can see in the middle is not equal. On the right hand side is another reference to our argument list, so we use right tack. And on the left is a constant, and we're allowed to have a constant array on the left hand side of a fork, so we'll keep that as it is. So now we've written the train, or rather we've written the tree structure. Let's write it down in the session as a train. So top level we have a fork with the middle tine of partition, right tack on the right, and on the left we have something, so let's parenthesize just to be careful. It's a fork where the middle tine is not equal, right tack on the right, and a constant on the left. So apply that to my list and we see we get the same result, so that's good news. And what's more, if we have the boxing setting that turns trains into trees, then what we can see is the exact tree that I just wrote, expressed by the interpreter. Of course, you can simplify this slightly further by recognizing we only have one other constant which we could turn into a left argument. We could make the whole thing dyadic and then recognize our left tack function right tack and eliminate the tax. So now we have a really neat little fork, a little 3 train here called split by delimiter. It's very useful because if you want to split some array by a certain delimiter, it's quite easy to remember a sequence of 3 functions like this as a sort of compound word. So that's quite neat. Of course, we could have converted our one-liner into a defen first and used the sort of defen processing procedure I'd used before. And I'd like to do that just now on a modified version, just to make one extra point quickly. So this is a slightly more generalized function that can split on any of a set of delimiters. And I'm going to sort of rattle through this one. There's lots I would like to talk about. So get rid of the curly braces. Let's go function, but we're starting to go from crawling to walking now, so we recognize that and put a right tack in. So it's function, function, and then another big function. Let's go inside. Alphas will become left tacks, function, omegas will become right tacks. So it's function, 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 but we have another function here, so the overall structure is in a top. Okay, this still works. We're seeing tack, function, tack again, so we think there must be a way to eliminate those, but it's not going to be as straightforward, but it's not much worse. We can't just simply remove them because they swap the arguments around, but we have an operator for that, the commute operator. Now we've simplified it down somewhat. We have a slightly more generalized version of our fork. So there's a couple of examples and a couple of methods of writing trains from functions you've already made. One other reason you might want to do this is to visually bring together some functionality which, when you wrote it in sort of more traditional style, the functionality that was going on is separated out between functions and bits of arguments, bits of data, arguments. Babble. In this example, we have a function that asks, are there any of our left argument found in the right argument? Are there any of some in here are some words? Yes. The issue with this is it doesn't extend very easily. If we want to search for multiple words, well, I've kind of done it wrong because instead of searching for each of these words, it searches for the whole nested vector in here and obviously doesn't find it. But we can recognize function, argument, function, argument as on the top. Bring the outermost monadic function inside and then apply for each of our search words, but we need to also enclose our argument. So this is kind of more what we were looking for. We found some, but we haven't found thing. If we wanted to make the same modification on the traditional APL, then we have to put each on this side, and we have to put each enclose on this side. So, there's a little bit extra work involved when you're generalizing that function. There's one other benefit in this specific example. So I've made my workspace ridiculously small, and I've created a variable which takes up most of the workspace. And what this means is when I apply this function, searching for a bunch of words in my large array, I get wussful error. But if I use my train where the functionality has been brought together, I'm actually able to run it, even though these two expressions have the exact same functionality. And that's because in this case, we are generating the find vector for each of these words and then having to store them somewhere in memory before afterwards reducing each of those vectors which have been stored. In the second case with our atop, in the second case we've kind of fused the loops, and in each case we generate the find vector and reduce it to a number. We generate the find vector, reduce it to a number. Generate the find vector, reduce it to a single number, and so on, hence using less memory. The more astute of you may have recognized this isn't exclusive to trains. We could have got the same benefit by bringing the functionality together into a single defin. So that's just one sort of particular quirk. And those were a couple of examples of when trains come out quite nicely. But sometimes a train is a pain. Sometimes just for the practice you're kind of generating trains and you find that something just won't reduce into anything very elegant, it just looks ugly. And one of those cases is when you have long sequences of monadic functions which cannot be made dyadic. So here's an example. This function sums up all of the prime numbers up to its right argument. Okay, so we're going to use our sort of defin modifying method to go through this. So from the right, function omega, well, we know what to do with that by now. Iota, but monadic, so that's on the top. Just to be safe, we'll parenthesize it. Jot.mod selfie is one monadic function, so let's wrap that just to be safe. Then we have 0 equals is a fork, and dialog passes trains from right to left, grouping in threes for us, so we don't have to parenthesize this one. But the next function is monadic, so that becomes the top, so we should parenthesize it. You can see where this is going, right? 2 equals is a fork, so that's fine. Where monadic, so let's wrap it, and yep, there we go. We've managed to convert our defin into a train, but it's gotten significantly uglier and more difficult to read, really. There are some things we can do, like we know this is only being called monadically right now, so let's get rid of the right tack. We can make this whole thing into a fork by instead of doing a selfie, doing iota jot.mod iota, and this allows us to remove parentheses, but now we're doing iota twice, so that's like twice the iota work. A plus slash here can be turned into a 1 base, but that's just a golfer's trick, so it's not really going to be any good in production. And lastly, we could bind these two monadic functions with normal function composition. So it still works. We've reduced some of the parenthesizing, but our resulting train is exactly the same length as our original defin, so the golfers aren't even happy. And frankly, it's a bit less readable. We've also duplicated work and used a bit of a trick here that is also less readable to the lay APLer or someone who isn't super familiar with golfing tactics. So trains aren't always the best. They're also not the best when you are wanting to use the slash functions. And this is because APL overloads the slash symbol, right? It can either mean replicate, so let's have 2 of each of those, or it could be a windowed reduction depending on the context. And this becomes annoying for trains because this version, the operator binds to the function more strongly. Okay, to give an example, let's do a really simple one, like I want to merge my comma separated values. Yeah, okay, let's make it small. So we have some comma separated values and we want to merge them. So let's do something, reduce our right argument, and that's not equal. Not equal, reduce our right argument. So we get 1, which is annoying because if I wrote this as alpha not equals to omega, reduce omega, so we don't need that. This is the behavior I want. I want to get rid of the commas and merge the whole thing together. But my train didn't work, and that's because the slash bound to the not equals first, creating a not equals reduction atop right tack. And so you ended up with 1 because these aren't really equal to each other. Yep. So one more example just to show you how annoying it is the one I just showed. This removes leading zeros. Let's use our old technique we've been doing so far. From right to left, we can see constant function, what would be right tack, but our constant can't be on the right, so we can easily just swap this around, right? What was that? Sorry. Not equal to right tack. We're gonna, sorry. I'm getting back on it. Right. Okay, so that's a fork, so that's fine, but this or scan is a top, so we'll have to parenthesize that to be safe. Luckily, whoever wrote the defin has done the swap for us, so we just need to isolate this, and omega becomes right tack. So our function works, but it's got longer. I'd say it's probably slightly less easy to read. And on top of that, we have this very worried face in the middle. So if you're writing some function trains and you see a worried face like that, just look at it, looking back at you, asking why. Are you sure you want to do this? Okay, another time when trains aren't really the best. Juxtaposing arrays, and that's because we don't have a juxtaposed primitive in APL. What I mean, again, I'll demonstrate with example. That's how I like to do it. So our plus minus fork, once again, if we use catenate, we extend the first axis. And even if we use catenate first, if we use catenate, we extend the last axis. And even if we use catenate first, we extend the first axis. And in both cases, we probably want to separate our pluses from our minuses. And so we'd have to probably process the result afterwards using the dimensions of our left argument or something. One way of juxtaposing arrays in a train is to embed a defin as our middle tine, alpha omega, and then we increase the depth when we do the plus minus, so we can get some kind of reasonable result for a high rank plus minus. Or some people might want to increase the rank. So if you do a mix with sort of procedure here, then our matrix plus or minus 2 becomes a 3D array with 2 matrices inside. So both of these are quite reasonable behavior, but you don't get the nice, elegant sort of train out, which isn't as nice. What else makes trains a pain? Side effects. So because you can make a train out of any type of function, of course you could have a defin with side effects as one of your tines, or a tradfin that does all kinds of things. Most of the time you probably don't want this in your trains because it's probably going to be harder to debug. Recursion and conditionals, again, slightly difficult to manage. So for side effects, here's an example of a train that actually is somewhat useful in and does have side effects, kind of. This is a function which reads a file as integers. Okay, so I've got a file that just says ABC and some new lines. It's in the top, and what it does is it ties the file, reads the file in as integers, and returns what was read in, and then immediately unties the file as well. And one of the benefits of this specific atop is that you don't increase the next default tie number, and you don't have to create a separate temporary variable storing a tie number that you then use later. So this is kind of neat use of a train that uses quad functions and interacts with the file system and whatnot. What else can't you really do very straightforwardly? Recursive calls. So in a defin, del refers to the function itself, and in a tradfin you can use the function name, or maybe gotos or something. But in a tacit function like a train, how are you going to refer to the function itself? We don't have a way of doing that. Some recursive calls and conditionals can be rewritten either using the power operator or using some kind of reduction. So there might be ways around in some cases, but obviously apart from for amusement, you're kind of jumping through hoops for almost no good reason here. I've provided a very arbitrary stupid example just to demonstrate the point. This function decrements the right argument until it's a multiple of 5. That sort of procedure can be rewritten using the power operator with a function, and then that whole thing can be made tacit like this. So the right operand to power is another tacit function that happens to refer to our argument, the argument of the inside composed function rather, which is the argument that gets fed back into the function that uses power. So, here's a kind of workaround that kind of works, it's not so great. One thing you can't do at all is have arguments freely floating around in the operand. So there isn't really a way to convert this defen. Other things are like error handling, multiple inline variables, basically anything more complicated than a short, pure, simple function. You obviously want to break it up into things. Trains are kind of best when either you have short, simple idea that can be expressed neatly as a train using primitives usually, or your overall function is still relatively, pure and simple in that it takes arguments as input and produces an output without side effects, but it also happens to fit the train structure of either an atop or a fork. One way to sort of think about when trains are appropriate, to my mind, is if we consider the vocabulary of APL as the primitives, these are your sort of basic words, then to me, a train is more like a compound word. So an example, a way to think about this is we don't have a primitive for the range. There is no word in APL for range, as it were. But we can make a compound word. We can use a compound word that we call max minus min, right? And that works quite nicely. And that's, I think, the sort of language as a tool of thought aspect that trains provide, right? Extending that idea of a notation as a tool of thought, where we had the primitives that were very, they're very mnemonic and they do these very versatile things. We can have trains which are compound words, some of which are also very mnemonic and do specific things. So many of the examples I've shown so far are viewable or searchable on AppleCart, which is a sort of searchable table of all kinds of APL expressions that are generally quite useful. I'm going to show a couple more sort of quintessential, if I was making a mixtape of the trains, desert island trains, these are some of the ones that I'd show. In the meantime, if you're watching on Dialogue TV and participating, perhaps talking with Adam, I invite you to send in a one-line APL expression or defen, hopefully without the caveats that I've explained a second ago. Those caveats can also be found on the defens page. Send some in, and I'll have a go at using the sort of tree writing method to convert those into trains, because even though I've sort of been demonstrating this, it could feel quite arbitrary, like I have hand selected some specific expressions and defens to show particular things, but the method is very general, because far from being, some specific quirky syntax, function trains are actually fundamental building blocks and reflect the way that APL works. So you can send those in while I know there's a delay, so I'll just talk about a couple of these. So here we have the is it a palindrome train, race car is a palindrome, race cat is not. We have the is my array diagonally symmetric train. So does the transpose match the original? Is it unique? Does it have unique major cells? Is the unique match my original array? We've got obviously the classic split by delimiter, which is one of my favourites. I've started taking to calling it the beaten up face train, because if you imagine the middle tine as a sort of nose and mouth, then it kind of looks like a guy who's had his face kicked in a bit. Don't read into that. We have the extended one where his face is blown up a little bit, but it allows you to use multiple separators. We have the mean average, classic train, modified mean average, and you can also force errors, not force errors, but generate errors on empty vectors by binding times with divide. exclusive range. I guess it's negative the exclusive range, sort of 10 minus 3 not including. Monotonically, that's the inverse probability, not bad. Plus and minus, definitely a classic, one of the greats, one of the all great trains apart from the juxtapose issue. This train scales the elements of its argument so that the sum is 1. It's a kind of normalization. This one is one of my favorites in terms of its functionality. For its brevity, it's one of those cool expressions. Convert a decimal into a top-heavy fraction, so 1.375 is 11/8. This version converts into a mixed fraction, so 1 3/8. And that's kind of neat because then we can use computer magic to generate a rational approximation of pi, which is kind of silly, but there you go. If you're ever discussing internal representations of numbers of computers, then this could be one thing to discuss if you're teaching people. So we've have had a submission. I have prepared one final example if no one did, but this is one person's one-liner, which I'm just copying now. Alpha. Thanks, James, for sending this in. James Heslip. What a ledge. So, I'm guessing this could take, it looks pretty scalarish to me. 0 equals 1, so it's multiples. So this is an appropriate argument. Multiples 5, where pick the first multiple of 5, omega picked by where. Oh, okay, but you don't want to include it, right? Yeah, you don't want to include 1 because prime numbers, right? Okay, I see what it's doing now. So let's go for multiples of 7 in 7 plus iota 20. Oops. Is that right? Or is it the other way round? I'm being a derp right now. I knew this was a risky strategy. 0 equals omega mod alpha. So really maybe we want the iota on the left. Right? No, but it's omega picked by, so you definitely want an array. Well, either way, we can definitely turn this into a train. Doop. Okay, let's get my pen and paper back up and go for this. We got one more afterwards. Timing's not bad, so I'll go for these. So, from the right, okay, we've got lots of submissions now. Oops. All right, let's pin this. Oop. From the right, 3 train, another 3, and a top. So it would be a top. Blasted swap. Okay, that's monadic. I got picked by all of this. So overall, this is definitely a fork, where the outermost top tine is a sort of pick selfie, so pick swap rather, not selfie, pick swap. On the left, we're seeing a reference to a right argument, and on the right, we got a bunch of other stuff. And the other stuff is monadic pick, a top, iota underbar, a top. This is a fork, so it's equals, and on the left we have 0. And on the right we have another fork with mod, reference to right argument, reference to left argument, which I guess we could turn into a swap, but I may or may not. Let's see. 5. So topmost is pick swap, left argument there. On the right is pick a top. In fact, since that's on the top, we probably want to parenthesize to be safe. A top where, and then it's a fork, so let's not worry. 0 on the left, on the right another fork, right argument, left argument. Oops, and don't forget the 1 plus. So there's that one. Sorry it took so long. But there's the train as a fork, and we've obviously got the ability to make that a swap. And is there anything else? That's as good as I want to get with that one. Let's move on. Sorry, Adam, do you mind? I can't read the submission from... Oh, you're typing something. One iota swap. You mean underbar? No, that's not to do with the argument. Instead of pick iota. Sorry, Adam, I'm not quite getting what you mean there. Is this for the current one? Like, but it's a where. One iota swap. So then it becomes a fork, which means we can get rid of these parens. Is this the idea? I'm not seeing it. Oh, except for that's a top. So, no, it's not. Fork. Oh, one iota swap, dingus, instead of pick. One iota swap instead of pick where. That's a top. Yeah, instead of pick where. Nope, I'm not doing it right. Instead of pick where, it's one iota swap. Okay, let's isolate this just to be sure. I'm with you now, I'm with you. So now we have function, constant. We can get rid of more parens. Adam's just trying to help me simplify this, and I am being obtuse. So don't worry about it. Give me one more example before we finish. Longest delim. Well, this one's quite a healthy size, so let's go for it. Oh my, it's a lot to type anyway. Alpha, and then we already have our famous train inside there, so that's nice. And it's already made of trains. You know it's going to be a challenge. I'm not confident. I'll just say that about doing this one. Alpha is so long. We've got the same thing twice, so it could be an over. Right, longest delim. Is this longest sequence of a delimiter? Let's test. So like, say we got comma, C, comma, comma, A, comma, 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 B, comma. Okay, no, maybe I should actually look at what it's doing instead of just reading the name. Sorry, Jonas, I apologise for butchering this. Right, so split by delimiters, and we get the one out of there, which is the first downgraded shape of each of these. Oh, it's the longest thing that is split. So okay, right. So you split them up and get the longest one. Yeah. It's a bit similar to my max lim from near the beginning, right? So the longest part, the longest chunk is ABC. Right, I'm with you. You gotta make it hard. Right, first of all, we have literally, just enough time to explain all this. First of all, you've given me square bracket indexing, which obviously is a special syntax in APL. It doesn't fit with the rest of the monadic dyadic structure. So what we have to do first of all is take everything out of the square brackets and flip it around so that we're using squad. So we're going to take everything there. Let's parenthesize to be clear. And you're using a, oh, is that insert? Oh no. Son of a, how do we get rid of insert? Uh-oh. Killed my computer. What I'm going to say now, if this doesn't come back immediately, okay, we're all good. We're all good. This is embarrassing, but it's fine. It's the end of a webinar that's already too long, so let's not stress. 0. Oh, not again. I've accidentally turned insert on, which is just inconvenient, and my keyboard shortcuts are sending my computer to sleep, so I'm just going to not worry about it. Right, we take the inside of this. Instead of having, yeah, I know, right? I really need to get rid of insert. There we are. Right, instead of having square bracket indexing, we're going to use squad. We're going to take the thing that we were indexing by and make sure to enclose it, because indexing something about rank. Hope this works. Right, we're still good, bit more functional. Do the partition once. Yeah, I know you can factor out the partition as well. In fact, is there any external reference? No. So the whole thing can become an atop, as it were, right? Almost. Yeah. The whole thing could become an atop, like this. So then this whole thing becomes omega, and this whole thing becomes omega, right? I think so. I'm going to enclose all of that. Take the omegas out here. So close. There's a left argument. What function are we looking at? Oh, it's not an atop. Sorry. How close are we? We're pretty close. I thought it'd be this, atop this. It would be an atop if I isolated it from the functions. Right, there we go, using round parens. Let's keep going. So we factored out one of the splits, that's pretty nice. And we got this right tine of a fork, and let's go back into here. Start by using our old defense method. Our omega, we're experts now, that becomes a right tack. This one we have to be a bit more careful about, but I guess to start with we could just make the whole thing a defin like that, and the function still works. Sorry. Now we go deep into here. We're looking at omega. Oop. We're looking at omega, that becomes a right tack. Function, that's bound together. Function. Am I right? No, because that's monadic in list. So shape each atop that. Monadic in list here. Downgrade it. Also monadic. See what we get? Pick. And then enclose. Okay, I mean shape each. So let's get a scalar out instead. I'm not sure exactly what benefit that has. Thank you, Adam. Replace in list shape each with just this. Okay, good stuff. We're most of the way there. It's already a train, right? So we did it. I didn't make the tree. I did lie about that. I went straight for the defins because it was a defin. And I had to do a bunch of shuffling around, so I apologise for that. If you want, yeah, I don't see myself simplifying this too much. Last thing, and then we'll end, because actually it's 2 minutes to 5, so I probably won't even do it, but I'm looking at this atop that. It's a big thing. We've got, okay, squad, right tack. On the left hand side, it's enclose, atop disclose, atop grade down, atop match each right tack, and then that is all atop our classic train. Alright, so there's not equal and there's right tack. And so if we take the whole function without any arguments and use our tree thing, how close did I get? It's an atop. Okay, I've written it slightly differently because it's this thing atop this thing, right? Classic train on the right, and then here's all of our tops. They're ridiculous, and also when I do this, I bind operators to functions beforehand because it's easier to write. That worked. Okay, got on for too long. Thank you very much, those who sent in functions. That was quite fun actually, even though I sort of struggled a little bit. I will summarise and shut up and let everyone go home. Trains, inline anonymous trains are best for short, pure, simple and idiomatic functions which become very recognisable, and some of these are quite well known, the ones that I've presented today. There are two types of trains, and all trains are like this, and then you can just break them down. So that's 2 trains of tops, 3 trains of forks. All of the information and some more is available online. Here are the links. Search for Apple Wiki Trains or Deafin's Tacit. The next webinar is next month, 20th of February. Haven't fully solidified the title, but it's definitely going to be about making APL code run fast. I'm not sure to what extent that'll be APL code you already have, making it faster, or just making sure that the things that you're writing are sort of, written in such a way that you know they're going to be fast, potentially get faster in the future, or stay fast. I don't know. I'm probably saying too much considering I don't know what all the details are yet. But in any case, I'd like to say at this point then, thank you everyone for watching. Thank you for those who participated in the chat. And that's it for today's webinar. Thank you very much.